All right, we've officially made it to the last lesson of chapter 1. We're still looking at a little bit of derivatives though. Usually what's happened at this point is after the last lesson, a couple people have noticed already or maybe looked ahead a little bit and started to recognize what the patterns are for finding the derivative of some of our simpler functions. Later on in this course, we still have to do much more difficult derivatives, but some people might already know these. Now, if you don't yet, that's fine. That's not something to worry about. I'm going to show you what these are without actually explaining how I'm doing it. So if you already know, that's great. If you don't know, my guess is you'll probably figure it out as I do these 3. If you still don't know, not to worry, because very next lesson, I'm going to show you. But I don't want to give it away. I want to see if you can see the pattern. So this first function here is x to the power of 5. And that's not one that we'd want to do the long way. We did that cubic one last lesson, and that's enough to expand. We really don't want to expand x to the 5th, but we don't need to. The pattern says that our derivative is just 5x to the 4th, and you're just done. Okay, so the shortcuts that you can notice to do these derivatives allow us to just write the answer down immediately. For this one, it's a little bit harder. But again, a massive function, right? Not something that we'd ever want to try and do using first principles, using the long way. But the answer is just 14 x to the 6. So maybe you see the pattern now. And then this guy, h prime of x, this one has 3 components to it. The answer here is 6x plus 5. And that one's a little bit more complicated. So we'll leave that one to hang with you for a little while and see if you can figure out all the reasons. Again, we're going to address these later. Okay, honestly, I just don't want to give away the secret just yet. I'd rather you look at it for a minute and try and figure it out yourself, and we'll go from there. So introduction to derivatives part 2, we did part 1 last class. And here's where we're going to start. It says determine the derivative of the function using first principles. So first principles is the long way. First principles means use our limit definition, which was taking our difference quotient and letting h approach 0. So really what that was doing was it was taking our secant line and letting it approach a tangent line. Okay, so whenever it says, and on the test it's going to say this, using first principles, then you have to write this line. Okay, if I ever say using first principles, you must have that. If I don't, if I just say state the derivative, then you just put the derivative down like this. Okay, but if I say first principles, and on this first unit test in particular, I guarantee I will, you have to write it out the long way. You have to do this definition of the derivative. And this is all about showing your steps clearly and making it obvious how you get your answer. It's kind of like our vector proofs from way back, right? We're trying to be very specific about how we're calculating everything. All right, let me get started here. F of x plus h means wherever we see an x, we should put an x plus h. F of x was just the root x. And the problem would be, as has happened every time, if I sub in 0, which is what we're supposed to do to evaluate the limit, you'll get 0 over 0, and we get our indeterminate form, and that's no good. So the shortcut, not the shortcut, the trick for these ones, the method, is to rationalize, right? We have roots, and whenever we have roots, our method is usually to rationalize. So I'm going to multiply top and bottom by the original numerator, right? It looked like this, but I'm going to switch the sign. It used to be a minus, and now I'm going to multiply by a plus there. And exactly the same thing on the bottom. And remember, the reason that worked was that technically now we're just multiplying by 1, and we're allowed to multiply by 1. To be a little bit careful with all of the expanding here. I think actually going to take a step and just do the denominator first, because remember we didn't expand this one. It's the top that we're interested in. The top's more interesting because because of all the square roots, and they're going to cancel. We have the conjugate there, the plus and the minus. Okay, I'll put some arrows in. I hope this doesn't get too messy. Everything in the first by everything in the second. So root x plus h times root x plus h is just x plus h. And then root x plus h times root x just looks like that. And we'll do the next one. And it looks like my fraction isn't going to be big enough. There we go. Minus root x times root x plus h. And that was the point, right? To get that one there, those two terms, this one and this one, are plus and minus versions of each other, so they're going to disappear. And then minus root x times root x would be a minus x. So if we start combining some things, or I guess canceling some things in this case, those middle terms disappear. There's also the x and the minus x there. So they're going to disappear. It leaves you with just an h on the top, which is fantastic. Right? We've gotten rid of so much, which is what had to happen. Right? We absolutely needed that to happen. It was the h on the top and the h on the bottom that were causing our indeterminate form. But now they cancel. And you're left with 1 over. And if we sub in our 0, so now I'm evaluating this limit, so I don't write that part down anymore. It's just root x plus 0 plus root x, which is around 1 over 2 root x. And that's our derivative. That's a tough one. Now, one of the interesting things is, if, and this is going back to where we started, right, when we did these derivatives, if you knew the pattern here, if you understood what was going on there, does that idea apply here? Okay, so if you figured out how to do that warm-up, think about this one here and think if this idea still applies. Okay, that's a tough question for you there too. All right, here's our next one. Actually a little bit simpler, but I got a couple parts to it, which is going to lead us to where we're trying to head today. It says determine the derivative of the function f of x using first principles again. So I have to do it using first principles. First principles means use the limit definition. One of the questions that sometimes comes up is, do I have to write limit down every time? Because I just keep writing it down and I'm not doing anything with it. And the answer is yes. You have to write this down until you actually make the substitution. So make sure you have that. F of x plus h would be 3 x plus h squared minus 3x squared all over h. Now, by the way, I should have mentioned this a second ago. I think we probably know what the answer is. I think we probably know the answer already. Because again, if you recognize the patterns from the beginning, the derivative of 3x squared is 6x. So I can do that in my head in less than a second. So I know what the answer is, but it says to do it using first principles. So I have to go through this procedure that I've got in the green. But I know that my answer better be 6x when I finish. Okay, this is helpful. It's nice to know the answer. But it becomes almost like I hesitate to say it, it's almost like a trig identity kind of, isn't it? You know what the answer is, you just have to try and muddle through all the algebra to try and show it. So you need this, but the fact that we know what our answer is should help. If I expand this, the 3 stays. X plus h squared means x plus h times x plus h, which will get me to there. And let's be a little bit, well, no, let's not. Let's take our time. We'll show everything here. I'm going to multiply the 3 through the bracket. So 3x squared, 6xh, 3h squared, and the minus 3x squared still kicking at the end. H there. This has happened, I think, every time, even in the last one, right, with that square root function. The first term, the 3x squared here, and the minus 3x squared there are going to disappear. And factor out an h on the top. And that's probably good news. You can see the 6x there now. The h's will cancel, and I'm going to sub in my 0. So here's where I'm making that substitution, which means the limit is finally gone, and the answer is 6x. And if this is a little bit frustrating, it probably should be, because we wrote down an awful lot of stuff, and again, we knew that answer of 6x right away. Okay, so we knew the answer, it just took us a while to get there. Okay. It says determine f prime of 2, f prime of 0, and f prime of 2. Negative 2, 0, and 2. Excuse me. Not a hard question, actually. We can do this one relatively quick. F prime of negative 2 means sub in a minus 2 into this function, right? So 6 times negative 2 is just minus 12. Remember what that means. That's the slope of the tangent when x is minus 2. So the slope of the tangent is minus 12. So relatively steep and going downwards, right? It's a negative slope. If I do f prime of 0, that's 6 times 0, that's 0. So we have a slope of 0. That's very significant for us in the course. Whenever you have a slope of 0, that means the slope's horizontal, which means you have a horizontal tangent. That's pretty significant. That actually indicates that you must have a maximum or a minimum at that point. And f prime of 2 would be 12. So we were able to get the 3 of those. There we go. So last part here, it says sketch f of x and f prime of x. You gotta remember what was f of x. F of x was 3x squared. And now f prime of x is 6x. Let's change colors there. I just want to graph both of them. One of the things we want to look at today is this comparison of the graph of an original function compared to the graph of the derivative and how they relate to each other. So 3x squared is a parabola, and it's a very simple one actually. It's our original graph would have been just x squared, and we've multiplied that by 3, so we've got a vertical stretch by 3. No translations though, right? It hasn't moved left or right or up or down at all. So our vertex is still here at 0, 0, and I don't know if you remember the step pattern well or not. In this case, we've multiplied our step pattern by 3, so we're going over 1 and up 3 to get the next point. Excuse me, and then we go over 1 and up 9 to get the next point, which we can't fit. The other way, if you just wanted to graph this, you could just sub in a couple of values, right? If I sub in x equals 1 into this equation, 1 squared is 1 times 3 is 3, we get that point. If I do the next one at x equals 2, 2 squared is 4 times 3 is 12, so it's some point up a little bit too high. Okay. So this is a not particularly impressive sketch of a parabola since it's only got 3 points, but it's not bad. And then 6x it's quite easy. It has a y-intercept of 0, and it's got a slope of 6. So it's over 1 up 6, over 1 up 6 again. Oops, that's too far over. So we have a really steep derivative function. Oh, that's not my best effort, sorry about that. So there's the 2 of them. And what I'm interested in is comparing what the red and the green look like together? I mean, obviously one's a parabola and one's a line, right? So we've got significant differences there. But what's the significance of the values that we see? What's the significance of the slope and increasing and decreasing and that sort of thing? And there's a lot there actually. So let me see if I can try and highlight some of the things for you. Right here at the origin, and thinking about the parabola for a minute, so our original function, that's got a minimum there, right? That's our vertex. And so the slope right there at that point would have to be 0, right? It's a horizontal tangent. And then if you look at the green line, that's our derivative, the y value there, the value on the y-axis is 0. So it's telling you that the slope is 0. What's easier to see? Maybe if we look on the left now, take a look at the parabola on the left-hand side. Everywhere along there, that graph is going downwards, right? We'd call that a decreasing section of the graph. The slope of the tangent everywhere there is negative, right? If I were to draw a tangent line on, the slope of that line is negative. And so in turn, that section of the derivative function is negative, indicating that the slope is negative for all of those particular values of x. Whereas on the other side, now you've got this side of the parabola, which is increasing. The slope there is always positive, and so the green line, your f prime of x, is always greater than 0, which means that the slope is positive. So we have this relationship between each type of function. Specifically there, if you go back up to part B where we made those calculations, you can't see it on the graph, which was a little bit intentional. It says f prime of minus 2 was negative 12. Well, that's, if I go down here far enough, right there, I would have got to minus 12. That's actually telling you that the specific slope when x is negative 2, the specific slope is minus 12. So we get that specificity too, right? It's giving us exactly the value of the slope, and it's also giving us just the fact that things are positive and negative. Okay, let's try and apply that here. So this time I'm not giving you an equation. In fact, the equation would be a little bit difficult to come up with. You can come close, but I have to get the perfect one. Given the graph of f of x, draw a sketch of what f prime of x would look like. And again, it just says sketch, so I am not worried at all that this thing is going to be perfect. In fact, there's no way we're going to make it perfect. But there's a couple of aspects that we have to get right. First thing to notice is that f of x is quadratic. And if it's quadratic, that means that the derivative is linear. And again, this is based on some of the properties you've probably noticed now with the derivative. The degree always drops by 1. So if the original function was a quartic equation, the derivative of that would be cubic. The derivative always decreases by 1 as we go. So when I graph, or when I sketch f prime of x, I know I'm going to make a straight line. That's one thing that I know. But I want to be a little bit specific on will it be going up to the right, will it be going down to the right? And more importantly, well, not more importantly, also importantly, where is the x-intercept of this guy? And that's easy to find. Right here, at the vertex of the parabola, we have a horizontal tangent, right? There's our horizontal tangent right now. So right there, that's negative 3, I think. F prime of negative 3 has to be 0. It's got to be. You have a horizontal tangent. The slope has to be negative. So right here is my first point of the derivative function. Change that. I'm going to do the derivative function in blue. So that point is definitely on it. So what I'm wondering then is from there, I know it's a straight line, right? Does it look like that? Or does it look like that? Okay? And again, I can't do too much with the actual steepness, but I should be able to know if it's got a positive slope or a negative slope. The easiest way to tell, I think, is if you look at just look at a particular point. If you look at a point, say right there, and you imagine what the tangent line would look like. I'll sketch one in. There's the tangent line again. And the slope of that tangent line is positive. So if it's positive, then f prime of x must be positive. It must be above the x-axis. Similarly, on the other side, if I put a point there and draw a tangent in, the slope of that tangent is negative. So it would have to be below the x-axis. And that tells you then that your straight line would have to look like this. So it's all about that point in the middle, right? That's where your derivative is 0. To the left of that x value, the slope is always positive for the original function. Right? For that parabola, the slope of all of these tangent lines is positive. To the right of that x value, the slope is always negative. And you can see that here. So from here to here, because that line is below the x-axis, that's saying that our derivative is negative for those particular values of x. Okay. All right, so these are the types of questions that we actually want to do. We don't want to just keep coming up with derivatives over and over again. We will for a while, but we want to be able to do something with them. So this one says determine the equation of the tangent line to that particular function at the point 1, 5. Now, well, there's a whole bunch of things to think about, I suppose, in this one. Determine the equation of the tangent line. So a line should look like this. That's the equation of a line. So it's good news because it's linear, so there's not too much work to be done. We need to find two things. We need to find the slope, and we need to find the y-intercept. And this is a question that you guys did like crazy back in grade 9, actually. But of course, at the time, you didn't know anything about derivatives. Back in grade 9, it was determine the equation, and we would give you the slope, and we'd give you the y-intercept, or we'd give you some other information about the line, and you'd have to come up with those pieces of information. In this case, we were given a point. So the 0.15 is there. That's huge. We needed that. The thing that we need to find is we need to get the slope. And the way we get the slope at that point is by finding the derivative. The derivative tells us, it's specifically designed to give you the instantaneous rate of change, to give you the slope at a point. So we need to know the derivative. We need to know what f prime of x is. Now what I want you to notice in this one, this question says nothing about first principles. Okay? Those other examples we did a few minutes ago where it said, you know, determine the derivative using first principles. We had to use our limit property. We had to go the long way. This time we don't. So shortcut here. The derivative of 2x squared plus 3x is 4x plus 3. And we just get it immediately. Okay, the derivative is 4x plus 3. Now we need to know what the slope is when x is 1, because it was the 0.15, right? So we're going to take that 1 and sub it in here. So f prime of 1 that's just 7, and that's our m value. Right? The derivative was telling us the particular slope when x is 1. So now I can jump over here to the right-hand side. I can sub in my slope. Don't know the b value just yet. The way you get your b value is by taking that point and summing it into the equation. So your y value was 5, your x value was 1. And you solve for b. And that allows us to get the equation of the tangent line. So we're using the derivative to find the slope. The derivative gets us a slope at a point. And we knew the point, so we just sub that into the equation of the line to figure out the corresponding y-intercept. This is going to be a question we will do a lot, okay? Like it's a guarantee one on this test that you're going to have to find the equation of the tangent line, okay? The other thing to keep in mind, I suppose, we are going to jump back and forth between some questions where I say by first principles and some here where I don't. So just pay attention to the question. You could have done this by first principles. You could have got the 4x plus 3, but it would have taken you way more time than I'm allocating for this question, right? By not putting first principles down, I was assuming we could do the question pretty quickly. Last little thing to talk about, and that's the idea of a function being non-differentiable. We've already talked about continuity, and continuity meant, again, our informal definition was, does the graph just continue on? Are there no breaks in it? Well, we also have this ability for functions to be non-differentiable, which means you can't take the derivative of them. What's going to happen here, though, is for the most part, how does that work? Well, you can't take the derivative if you can't get a tangent line. As long as you can get a tangent line, you can get the derivative. If you go way back to the very first lesson in this unit, that bouncing balls activity, you remember how the ball bounced on the floor and then it would shoot straight back up again, and it created that corner at the bottom. And one of the questions was, could you figure out the instantaneous rate of change there? And you can't, because you can't draw a tangent line. And if you can't draw a tangent line, then you can't get a derivative. So here are situations where you can't get a derivative at a particular spot, okay? Only at a particular spot. So that corner idea was called a cusp. So your cusp is right there. And so we're saying that you can't get the derivative when x is 0 because it's impossible to draw a tangent line. A lot of people would say the tangent line would look just like that because it only touches at one point. But it doesn't work like that. Because if I could draw that, similarly I could draw that, and that's still just touching at one point. Okay, so there's no tangent that's possible for a function with a cusp. But if I'd ask you to get the slope right there, you could. Right? In fact, you can even tell on this one that that's just the slope of 1, I think, isn't it, for the whole line? So it's differentiable there. The only problem happens right there at x equals 0. Okay? So we're saying in this case that it's non-differentiable at a particular location. Second possibility, here's an example of an infinite discontinuity. Truthfully, any discontinuity means you're not going to be able to find a derivative. So this is a nice one because it's actually a very nice function. Right? Y equals 1 over x is it's a fairly simple function based on what we're used to now. But there's no point there. There's no point at x equals 0, so you can't get the derivative. So remember, I'm saying here this is non-differentiable. I cannot get the derivative at x equals 0 only. Everywhere else is fine. If I said find the derivative at x equals -2, we could, because there's a tangent line there, and we'd be fine. That could be done. Everywhere else it can be done, but at x equals 0, we have a discontinuity, and if there's a discontinuity, you can't get the derivative there. The last one, and this is a fun one actually, is a vertical tangent. So the graph you're looking there has a nice equation actually. It's the cube root of x. All it is it's like taking your x cubed graph and you're doing the inverse. So we write it as y equals x to the 1/3, or you could have written it y equals cube root of x. Right? Remember our exponent rules for being able to convert between exponential form and radical form. So this one says it's non-differentiable at x equals 0. So right here only, that's our only problem. And this is a different problem because I can put a tangent line in there. Right? This time I can draw a tangent line. Tangent line goes right there. Touches at exactly one point. It's nice and smooth to the curves. The problem this time is if you think about what the slope is. Horizontal lines have slopes that are 0, but a vertical line, we say that slope was undefined. And the reason was your slope is equal to the rise over the run, right? So that tangent line, that green one, clearly has a rise. It's going up and down, but the run is 0. So it's some number divided by 0, which is undefined. Now remember, I'm saying everywhere else there it's fine. There's no other problems on that function. But right there, right at x equals 0, that's an example where this function can't be defined. And if you're up for it, think about how you would take the derivative of that. You might be able to do that now. We're going to talk about it next class anyway. But if you can do it already, think about how you take the derivative of that, and that might help show you why the derivative is undefined at x equals 0.